Mortier from the University of Cambridge. Originally, she was scheduled to visit us in person, but now with the COVID-19 surge or the COVID-21, it is now surge in Belgium. This was not very wise, so we agreed that she would give the seminar online. So as you could guess from her name, Annelies is actually from Belgium. She studied at the University of Ghent. She did a bachelor and a master's in mathematics, but with an option in physics and astronomy. Then she went actually go teaching for a couple of years in high school. But she decided that was not what she wanted to do for the rest of her life. So she started to study astronomy at Leiden University. And then afterwards, she moved on a completely different topic to the University of Porto, where she did a PhD under the supervisor of Nuno Santos, under the supervision of Nuno Santos, sorry, on exoplanets. So she obtained her PhD in 2013, and then she moved on to the University of St. Andrews in Scotland. And then after that, she did another, or she moved to Cambridge, where she is still residing. So she's a senior Kavli Institute fellow in exoplanets, which is a fixed term for 5 years, but started in October 2018. So as mentioned, her specialization is exoplanets, and also today's talk will be about the characterization of or the properties of exoplanet hosts. So please, Annelies, you have the floor.
Thanks, Joris, for this introduction. So I'm going to talk about how we understand the stars in our search for another Earth, because very secretly I'm actually a stellar scientist working in the field of exoplanets. Now, well, Joris explained it all. This is me. I've moved across Europe in my hunt for a second Earth. Perhaps when I moved from Porto to St. Andrews, I overcompensated a bit for the climate. So Cambridge is perhaps slightly better in that respect. Now this is the obligatory plot when you give a talk about exoplanets. What you see here is the mass of an exoplanet in Jupiter masses versus the period, orbital period in days. And one can probably give an entire seminar just on this one plot, because there's lots of things that you can actually see from it. One thing to point out is that these are not all the exoplanets that have been found. Because this is a mass versus period plot, a lot of the Kepler detected exoplanets are not on here. So Kepler was a spacecraft that got launched in 2010, I think, 2010. And it was from the US, and it observed this one field in the north and found impressively thousands of exoplanets via the transit method. The problem is that the vast majority of those are orbiting relatively faint, between quotes, if there's galaxy people in the audience, around faint stars. So it making it really hard to actually follow them up and get a mass. Hence, they're missing from this plot. So they're in principle here on the bottom left. There's many more planets that we know of, for which we don't have a mass, but just a radius. Now, the other thing that is obvious from this plot is that there's no error bars right now. So several of these measurements do have quite significant errors still associated with them. But what we can see is that there's different families of exoplanets. So top left here is what we call the hot Jupiters, because the astronomers are not terribly original. So they're really Jupiter-sized, Jupiter mass planets that are so close to their host star that they are quite literally hot. So this This was the first exoplanet that was found around a solar type star back in '95. And that was quite a surprise because we don't have that in the solar system. And up until that point, the planet formation theory, as we thought it was, didn't actually consider hot Jupiters to be able to be formed. So the fact that we did find it and that we continue to find exoplanets that do not necessarily match what we see in the solar system, that does challenge the planet formation and evolution theories, so that we keep having to go back to the drawing board and make sure that it can explain all the exoplanets that we find. So there's the farther out Jupiters that we can finally detect there, and then there's a whole bunch of small planets that we call Earths, super Earths, sub-Neptunes, Neptunes, the Mercuries. All the names that we invent for them are really based on what we see in the solar system, even though several of these planets just simply do not exist in the solar system. The fact that there's nothing here in the bottom right, that is simply detection limit. We're pushing from top left to bottom right with detection techniques. So the fact that there's nothing here really just shows that we still can't do it and that we are pushing to get there. But the color, you've probably seen it by now, the color and the shape is based on the technique. And one thing that stands out immediately is that radial velocity and transits are the two main methods, and that's the ones that I'll come back to. What you also see is that there's a region here in the blue stars and the purple triangles that don't necessarily have a lot of detections with microlensing and direct imaging, but they do tend to probe quite a different parameter space. So direct imaging is our only direct method of finding an exoplanet. It's quite literally take a picture of an exoplanet. Currently, we're only sensitive to wide, far out, very massive exoplanets that are also very young, because the reason that they're very young means that they still have a very thermal signal, so they're actually brighter when you try to take that picture. But essentially you're trying to take a picture of a firefly next to a lighthouse, hence why it is so difficult for them to probe here. But direct imaging and radial velocity are now matching. They're getting together and we can start comparing them, and early results of that are very promising. But anyway, except for the blue, everything is basically indirect. So you do have to study your star. So here's my first motto: you can really only know your exoplanet if you know its host star. And at the very basics of that, it's simply because the majority of our detection and characterization methods are indirect, by studying the star and inferring what that means for the exoplanet. So some of you might know this, some of you might not, or want a refresher. The two main methods, radial velocity and transit. I'll start with the transit, where you look in photometry, you really just look at the light. If a planet crosses in front of its star, the light will dip and you learn something about the radius, because the bigger the planet, the bigger the dip, but also the bigger the star, the smaller the dip. So what you get is the planetary radius and also the orbital inclination configuration. But you obviously need knowledge of the stellar radius, otherwise you really only have the ratio between the two radii. If the transit comes back, then you obviously also have the orbital period. Radial velocity is then the gravitational effect of a planet orbiting a star, meaning that both of them actually orbit the center of mass. So if you have an orbiting exoplanet, your star will wobble. You measure that wobble and you infer the mass of the orbiting exoplanet, as well as its period and eccentricity. This method is restricted to only finding minimum mass, because you can't solve for the geometry. And you obviously also need the knowledge of the stellar mass. Now, a lot of the power of these methods lies in having them both, that you have a transiting exoplanet for which you then get radial velocities, or the other way around. We do it the other way around, but in the majority of cases, we have the transit first and the radial velocity second. Now, this is a good time to just plug SweetCat. Don't Google it on its own. You'll get a Japanese girl liking cats. But SweetCat is our catalog of stellar parameters for stars that have planets. We list every single planet host, and we give stellar parameters for every single one, but we do have a flag. It's off the plot, but we do have a flag saying whether it was done by us or not. So meaning whether the stellar parameters are one homogeneous set, yes or no. For radial velocity detected planet hosts, where there's radial velocities, it means there's a good spectrum, which means that we can analyze it with our methods. So we're over 95% complete and homogeneous for RV detected planet hosts. We're nowhere near complete in homogeneity for the Kepler planets for the faintness reasons. But if you ever want a trusted basis, this is done by the group in Porto, for which where I was a PhD student. And we're still maintaining this. Now, you have transit, you have radial velocity, so you technically have a planetary mass, you have a planetary radius. You can put them in this radius mass diagram. And one can then start to wonder, is there such a thing as a mass radius relationship? Well, I think this plot shows you that there's somewhat of a rough relation. If your planet gets bigger, so does your mass. Somewhat roughly, but there's no very clean relation, which does mean that if you do have a radius from a transit, you do still need to actually measure your planetary mass. You can't just infer it from having a radius, because there's no such thing as a clean mass radius relationship. The relationship that is plotted here is from Chen and Kipping, 2017. You can see that for the larger, more massive ones, it actually slightly tilts the other way, but the scatter, as you can see, is enormous, of course. Now, if you do the same plot, but you color code it with the precision, where the black is a more precise measurement than the gray, then you see that for the giant planets, not that much changed, but for the smaller planets, a lot of these points suddenly became gray, because it's really not that simple to get reliable measurements for these very small planets. So that is where HARPS Nord, amongst others, comes in. HARPS Nord is a high-resolution spectrograph, and high resolution as well as high stability. It's installed at the TNG in La Palma, Canary Islands. It's fiber fed, it observes in the optical, it has about the resolving power of about 115,000 for a bright star. These spectra are lovely. They are very, very pretty. So what you see on the left here is the TNG with its house below that on a day with clouds. There's quite often clouds on La Palma, but they tend to stay under the telescope, so that's a good thing. And on the right, it's a picture of HARPS, not HARPS Nord, but it's essentially the same thing. The HARPS was the first one and is installed in Chile. So for work, they sent me to Chile and the Canary Islands. One can't complain, can they? So the long-term stability of the instrument is what makes it amazing. It has a long-term stability of about 80 centimeters per second, and that is exactly what you need. Not just the fact that you have high resolution and get a one data point with a precision of 80 centimeters per second, but that you have that stably over a long period of time in order to map out the radial velocity orbits of the planets. That stability is the crucial element in that. So I'm part of the HARPS Nord science collaboration. HARPS Nord was built originally to follow up Kepler planets when Kepler then died. And so we switched focus to K2 planets. K2 then died. So we're now focusing on TESS planets. Concept remains the same. We're following up transit detected planets, and we focus on the smaller ones because we have an excellent instrument to do that. So this is again the mass radius diagram, but all the giant planets have now been cut off. What you also see on this is a couple composition curves. If you make the very rough assumption that your planet, for example, would be 100% iron, then that would be the red line. If it would be 100% water, just imagine that, then that would be blue. The green one, if it would be 100% silicates. So the two green dots here on the left, these are Earth and Venus, which are somewhere in between fully silicates and fully iron, of course, as we know. These are all the ones that have a mass measurement better than 3 sigma. And then all the colored dots is what we as a HARP-SNORT science collaboration have done and have contributed to that plot. So we're quite active in the characterization of small planets with full credit to the entire team that is listed here. And then many more for all the white dots, for which HARP-SNORT as an instrument was actually also used quite a bit, just not by us. So there's a couple things you can see: the fact that there's no clean mass radius relationship, also the fact that there is a fair amount of the detected planets on that same composition line as Earth and Venus, which is obviously really cool, and that things seem to change around here, which is that somewhat rough divide between what we call super Earths, slightly larger than the Earth, but still very rocky, and sub-Neptunes, smaller than Neptune, but not rocky and having quite a decent atmosphere around it. So that divide is roughly over here. Now, if you plot these exact same planets, so it's the exact same points as before, without Earth and Venus, they're now put in density versus orbital period, and the color is with the planet radius. The squares is what the HARP-SNORT collaboration team has done, and the dots is what the rest of the world has done. So a couple of things that you can see. One thing that you can see is that the points roughly go down, so you don't have that many low density small period planets, which is because of photoevaporation. If you do, as a small planet, get too close to your star, because of photoevaporation, your atmosphere goes away, and as a result, you become denser. So this plot quite nicely shows that. But what you can see is that we hold the record for the smallest ultra short period planets. They're all sub half a day, actually. Not quite sure you would want to live there. So K2141b is the shortest period small planet with a well-characterized radius and mass. Over here, Kepler 78b was the very first one we did with HARP-SNORT at the same time as a US team, HIRIS. The publications came out at the same time. And then this is TOI 561b, which is really cool because if you then look at the other end of the plot, then we're also really good at getting the longer period planets, long being very relative term, of course, just like faintness. And you see that one of them, TOI 561e, is also here. So this is an entire system. C and D are in here somewhere. But we probed both the very ultra short one as the long period one. If I would given this talk a couple months ago, I could have said that we also hold the record as the longest period one, but then the KOPS team came out with a transit of Nutu Lupi. If you haven't seen it, it's an awesome paper, it's an awesome result by Laetitia Del Rey, she's also Belgian. And this is one example where they had radial velocity first and transit second, basically hoping for it, right? You point your telescope there, you know there's radial velocity detected planets and you hope they'll transit, and they do. So that was quite an awesome find. So it's okay that they have the record now. I want to focus on K2263b. It's one that I did a couple of years ago. What you can see here is the radial velocity versus time. It's a 50-day, what we call sub-Neptune. So it's a small planet, but it does have somewhat of either volatiles or a significant envelope of waters, like low density material around a rocky core. The curve that is plotted here, we've threw two models at it. One was with Gaussian processes, and I'm not going to go into details. But statistically speaking, this is not straightforward to fit. As you can see, our data can be quite scattery as well. So it's not at all easy. And the longer period it becomes, the harder it becomes to properly sample entire orbital periods, just because of access to the telescope. And the fact that stars are seasonal, you can't actually observe them throughout the entire year. Now, from this particular planet, this far out planet, based on just its mass and its radius, you can start inferring what that might mean for its composition, which is very degenerate and not straightforward, but it's likely that it has a significant envelope or either water or volatiles, rocky core. And because of this, it probably means that it formed beyond or near the snow line in its own system and then migrated inwards in order to have this type of planet at the region where it currently is. Speaking of composition, so one thing that was very clear very early on when planets were found is this relationship with metallicity. If I say metallicity, I usually mean iron abundance. The reason that we usually mean iron abundance is because it's measured in the optical, and the optical is just filled with iron lines. So iron abundance and global metallicity, if you measure in the optical, it's a pretty good match. So what you see here is relative frequency of giant planets versus iron abundance. And well, there's no denying that this goes upwards. It's exponential. This is work I've done as a PhD student. I'm not the one who found it. This was found in the 90s already. But one thing we investigated in this particular work is what happens at the lower end. Does it remain exponential in the sense that you really do go lower in probability in going in lower metallicity? Does it become constant, which is something that at the time was predicted by planet formation theories such as gravitational instability? Or is there a drop in the sense, like, is there a lower limit? Is there a limit in your metallicity where if you go lower than that, you won't be able to form a giant planet? Essentially, at the time, the data wasn't strong enough to distinguish between all three possibilities, and all three were a perfect match. Well, not a perfect, were a good match to the data. So we don't know, and we still don't know. What is true, however, is that there's still no giant planets found under -0.7 in iron abundance. What is also true is that because of this relation, we do have a slight bias in our observations towards higher metallicities. So that is something to take into account. On the right here, you see work from the Lars Boekhaven in 2015 using Kepler, where the red was all the stars that they looked at from Kepler, and then in the blue, the ones that have small planets. And as you can see, we don't see the same effects. It's slightly differently plotted than on the left, but it shows the same thing. But you don't actually have that exponential increase. There seems to be no metallistic preference for small planets orbiting stars. This has been confirmed by several other people, several other works, that as small stars, small planets are concerned, they no longer care, just in terms of preference, and just in terms of the existing there. But it can matter in terms of composition. Now, metallicity is obviously complicated. I said that overall metallicity is relatively close to iron abundance in the way we measure it. But there's also a known effect that this is from Gala apogee, I think. So where you see the alpha abundance over iron, so alpha elements like such as magnesium, silicon, carbon, things that make up this silicate mantle in planets, right? And that if you go iron poor, you are actually enhanced in these alpha metals. So the ratio between iron and silicates in your star changes if you go to different types of stars. And then the obvious question becomes, does this influence their orbiting planets? Because the star was originally formed from the big cloud. It has that protoplanetary disk around it, which should have similarly chemical compositions. So the planets that are formed from that, will they be different in composition as well because of this different ratio between the iron and the silicates? And there's a couple papers that I point out here that are really cool to read. So this is the second planet that I want to point out from the HARPS-NORD collaboration. It was a collaboration between HARPS-NORD and Espresso, which Espresso is in the southern hemisphere, HARPS-NORD is in the northern hemisphere. But given that this was a K2 planet, that meant it was close enough to zero declination so that we could look at it from both hemispheres. So it has one transiting planet. You see it on the right here. So the blue points are all the points. The pink ones are binned. It's quite a nice transit detection. It has a radius of about 1.8. So that is relatively in the middle between the super Earths and the sub-Neptunes. And then on the left here, you see its corresponding radial velocity curve face folded, where the blue is HARPS-NORD, the orange and the green is Espresso, 2 different seasons, and the pink is again binned in phase. We also found a second signal in mean motion resonance that is obviously there in the radial velocities. We did all the checks we could think of that this was not caused by the star itself. So we think this is due to a planet, but if it's not transiting, that's obviously still very hard to tell. Now, what we did with this planet is that we ran some composition models, because the cool thing about this star, if you ask biased me, is that it is iron poor and alpha enhanced, quite a bit alpha enhanced. So we ran composition models on it, and the radius and mass as measured of this transiting planet are consistent with an iron planet having an iron core and a silicate mantle, where the iron core has a mass fraction of only 10%, which is about a third of what the Earth has. So the fact that the ratio in the star between the iron and the silicates is off can be reflected in the planetary composition, and the mass and radius that goes with it is fully consistent. So that is a pretty cool result. It was one of the first times that we showed it for a single planet that could be the case. Now, little gap here just to show what the issue is with getting small planets and characterizing these small planets. It's because the second motto, it's not just about knowing your exoplanet if you know your host star. We have trouble finding our exoplanets if we don't know our host stars. Just to back up what I'm saying, this is a histogram of all the planets that have a density measurement. So basically all the planets that have, regardless of their error bar, that have a mass and a radius measurement. You see the small planets on the left, large planets on the right. Now, if you would make that histogram of simply all the planets that have a radius measurement, you get this. It's a little sad. Now, for the giant planets, the majority of them, if you have a radius, we also have a mass. For the small planets, nowhere near that is true. Part of that is because several of these are around faint Kepler hosts, but part of that is also because it's really, really hard. Because in order to get a density, you need a mass, and for a mass, you still need radial velocity right now. If astrometry would catch up with us, then they can take part of it, but at the moment, you still need radial velocity for that. And it sort of seems like we may have hit the barrier. So what you see here is the semi-amplitude, so the amplitude of your sine curve of the radial velocity versus the year of discovery of said planet. So you have the first one over here, 1995, the first one around a solar type star. And you can see that it nicely goes down afterwards and then somewhat gets stuck around a meter per second, which is this horizontal line here. The color is color-coded with the precision on that semi-amplitude, so the significance of the measurement, which the darker it is, the more significant it is cut off. So several of them have significance higher than 12 sigma. But I cut that off just for clarity. And as you can see, for the smaller ones here and the ones that fall below the line, the vast majority of them are not at all what many of us would not call significant at all, of course. And there's a couple here that are more significant. These are radial velocity only detections that are still actually being debated in the literature, whether that was true or not. In the end, it seems that we somewhat have hit a limit. Now, part of that is because of instruments, of course. You do have to make long-term stable instruments. But still, the part of that is not the instruments, because HARPS Nord has been online for quite a while, has a stability of 80 centimeters per second, and with enough observations, you can get significant semi-amplitudes of lower than that in principle. HARPS has been online since 2005 and has a stability of 1 meter per second. In the meantime, there's Espresso, who has been observing for 2 years, who has a stability of 30 centimeters per second, and we're still not dipping under this. And then there's multiple other instruments coming online that go in stability well below that meter per second, but we're not breaking that barrier. And the reason we're not breaking that barrier is our lovely star. Now, it's the most problematic variability that we have in the data. Photometry suffers from it too. But radial velocity suffers from it slightly more than that. The picture that you see here is from our previous solar cycle. So from 96 all the way to 2006, this is what the sun looks like, our own sun. So it goes from relatively quiet to relatively active, moderately active if you ask some people, to quiet again. Now, if our sun is doing this, then it means every star is doing this. And it obviously affects your data. And whilst stellar variability is obviously super interesting and very extensive, like pulsations, I know you guys work on pulsations. It's probably the one type of stellar activity that we can actually handle in our data, but there's much more than that. It's very interesting, but for us, if you want to find an exoplanet, if you want to characterize an exoplanet that you already know is there because it's transiting, it really gets in the way of getting the signal out. Now, just to explain a little bit what parts of the problems are. So there's many more, but I'm just going to explain a couple. One issue is granulation. So if you've ever seen the sun in detail, then it sort of looks like this ginormous beehive, right? So you have all these convection cells that you see here on the left. This is a very old reference, but it really does the trick. So these convection cells, basically the hot plasma is coming out. So as an observer, what that means is that there's hot material blue shifted towards you. What you can see over here on the left, the big spectral line. And then the material sinks back down into the intergranular lanes, which then are then both darker and redshifted because it's moving away from you. It sinks back into the star. So you'll have less strong because it's cooler and redshifted material. Now, if you then average that all out and just look at the full surface, what you end up with is a slightly asymmetric spectral line and a net convective blue shift. Now, that in itself is not actually the problem. If this process would stay stable, then that's fine. Okay, there's a slight asymmetry in our spectral lines. It stays stable. We'll just deal with that. Now, unfortunately, that's not the case. These cells do change from time to time, but the biggest effect for solar type stars is that you have magnetic regions such as spots and the accompanying plages. They cover this convection, and as a result, you have suppression of convective blue shift, and that makes the radial velocity measurement vary with several meters per second for a solar type star. Now, these spots and these faculae, they appear, they disappear. They grow larger, they grow smaller, they actually move on the stellar surface as well, in the end creating a highly unstable effect that still goes with several meters per second. Now, one thing that we could do is that we just study the sun as it would be a star, because for the sun, via other instruments, we know at all times what is happening on the surface. You can take a better picture, you see the spots, you see the plages, you know where they are. So we can treat it as a star, compare it to what we see in order to try and solve this problem. So we've made this a cute little solar telescope. So on the right here, you see the TNG. And on the left is our solar telescope. So during the night, we observe stars with TNG. During the day, we observe the sun with the solar telescope, and they're both plugged into HARPS North, and we treat them as a star. So it's more cute if you look at it this way. So it really is tiny. It has its own little dome. It has its own little platform standing next to the big building over here. These are not giant people. These are very regular, normal people. So our solar telescope is really quite cute. Now, we've been operational since July 2015. It's fully robotic. We take 5-minute exposures starting at 9 a.m. till about 4 p.m., 3 p.m., 5 p.m., really depending on the telescope operator and when they stop. You do see somewhat of an effect due to the schedule of the telescope operators when we stop observing. We're not the only ones. We were the first ones, but in the meantime, HARPS also has a solar telescope. Newitt in the US also has a solar telescope, and Espresso is looking into it. Now, first thing, this is the data, the radial velocity versus time for the past 5 years. And we've confirmed that Jupiter is real. So we see Jupiter and Saturn and all the other solar system planets, but this is really just Jupiter. Quite clearly in our data. Now, if some of you currently are wondering why we see Jupiter somewhat with a year-like period, rather than the 12 years that it's supposed to be, it's because you're in the solar system. And as far as people on Earth are concerned, Jupiter actually does have a synodic period of close to a year. So you can, if you were an alien looking for Jupiter, you do have to wait 12 years to see one orbit. Now, luckily, we know the solar system. We can take it out. So this is not just Jupiter taken out. This is the entire solar system taken out, as if there would be no planets. So we like to say that this is the only data set where you're 100% sure there's no planets. We took them out, and it's the only star that you can actually say this of. For other stars, you can't actually say that. So it's still quite messy, isn't it? This is really just a little bit instrument, of course, an extraction, and the sun being the sun on a daily basis. So this is the same plot, just a little bit bigger to explain the issue. This is now clean. There's no planets in it. You can't go brighter than the sun. This is a very bright star, treated as a star. This is the variability that you would get. If you would overplot the sun, the Earth, the signal of an Earth around the sun, so our own signal, then this is this. So basically, if you try to characterize small planets, especially small planets in longer periods, you're looking for the blue wiggle in the black mess, essentially. And this illustrates our problem quite clearly. Now, one thing that helps is that the stellar variability is, as I said, it's not stable. And it is related to solar rotation. So what you see here is something that I've worked on. What we often do is that we get our time series data and we make a sort of Fourier spectrum from it, what we call a periodogram. So it basically gives you power or probability versus period, telling you all the significant periodicities in your data. Now, you can take a data set and make that periodogram, add a data point, do it again, add a data point, do it again, and so on, and so on, and so on. So this is what this plot shows. It's in 3D, so you have period on the x-axis, you have time on the y-axis, just adding a different data point all the time, and the color is the significance, is the power, is the probability of your periodogram. The darker, the more probable. So one thing you can see is that the solar rotation around 27 days over here, getting really strong and then getting less strong and strong again. When it became less strong, the harmonic took over. So basically half of the rotation period is also really clear. A third of the rotation period, which is off this plot, also becomes apparent after a while. So clearly the scatter that you saw before does have some sort of periodicity with it. But if you break that up into semesters, so this is the first 6 semesters of HARPS Nord data, same plot, but just with reduced data sets. One thing you can see is that the sun doesn't seem to agree on what its rotation period actually is. So some of them give 27 as the rotation period, others give it as 30, some go as faint as 25. Some show this harmonic, others do not in a semester. I can assure you that the sun is still rotating at the same speed throughout these 3 years. This is really just showing how unstable this is, and that you don't get a clean rotation period signal from it. And as such, it's not as clean to model it and take it out of your data. Now, the other thing that you could notice if you have the good eyes is see that the actual probability values are pretty different. So if we were to put them all on the same, other way around, if we were to put them all on the same scale, then it looks like this. That's not too weird. The first semester was actually our most active semester. We started observing in 2015, which is after solar maximum, when we were going into solar minimum. So by the sixth semester, as compared to the first one, there's not actually that strong variability, but look at as a semester alone, then obviously it's still there. So both in amplitude and in phase, these signals are quite unstable and quite variable, which is a good thing, because if you observe for long enough, the planet signal at least should stay stable in amplitude and in phase. So that's one way to actually dig it out of the variability. We do have indicators of stellar variability. So one thing is just to look at the spectral lines. If a planet is causing the radial velocity shift, then your spectral line itself stays the same and just wobbles back and forth because of gravity, right? If it's the star creating this radial velocity shift, it usually means something in your spectral line happens and the shape of your spectral line is different. So what is plotted here is a periodogram of the radial velocity speaking at rotation period, half of it, third of it. And then the width of the spectral line, which is speaking somewhat at the same places. So clearly, in case we didn't know that yet, this is due to stellar variability, which of course for the sun we knew. Now you would think if their periodicity behavior is so similar that radial velocity and fluid half max would have quite clean correlation. Unfortunately, it does not. There is somewhat of a correlation. So the blue is all the points, and no, that the black is all the points, and the blue is bint per day. And whilst you can see somewhat of a correlation, it's not actually significant, and the majority of it just looks as a blob. The reason it looks like a blob is whilst it shows very similar periodicity, it's not actually on the same time scale. So there's a time lag. There are a couple out there where you can see it by eye. If the radial velocity variations go quasi-periodic, the fluid half max by sector, and any indicator we've looked at lags behind with about 1, 2 to 3 days in its variability, which means that they have a very similar periodicity structure. But if you want to plot a correlation, the whole correlation would be very much blurred out. Which is unfortunate, because in order to catch such a thing, you need very dense observations, which for stars is usually not the case, unfortunately. The reason for these correlations is mainly the spots, correlation with the indicators, I mean. The reason for the variability is not mainly the spots. So if there's a lot of spots, to some level, we can take that out because it does correlate quite well with our indicators. In the middle here, you see the spot fraction of the sun and the plage fraction of the sun over the same time scale as you have here. What you see here is slightly complicated. I split the data set into chunks of 60 days, overlapping 60 days. And then I looked for the correlation coefficient in blue, without just the correlation coefficient without a shift, and the Pearson and Spearman correlation coefficients. So blue, red, and cyan thing, they do overlap quite well. And then green is if you look at a correlation coefficient, but includes that 2-day shift. And as you can see, several of them go from not at all correlated to suddenly being really significantly correlated if you include that time shift. The other thing that you can see is that the strong correlations do go together with the strong periods of having spots on the surface. So it's mainly the spots, but even if we have that, we still can't break that meter per second barrier because the rest of the variability comes from faculae, granulation, supergranulation, and all sorts of things that we don't well understand. So I want to quickly highlight what my PhD student is doing, Florian Lienhardt. He's working on a new extraction technique called ZLSD, standing for Zeeman least squared deconvolution. His first paper has been submitted, the second one is in prep. He starts with a very careful pre-processing of the spectra because we found that even if you only improve by 5 or 10 centimeters per second, it's already worth it because that is also the size of the signal that you're looking for. So he does a very clean and careful processing of the spectra that you will be able to read in the paper once it comes out. And then use this LSD, or applies LSD. Basically, we use a theoretically motivated line list from the VALT, the atomic line database, where we have predicted wavelengths and depths of all the lines, and you basically correlate that with your spectrum, and then an LSD profile comes out. It's not too dissimilar from the current cross-correlation technique. That profile comes out, you fit it with a Gaussian, which is because we know it's asymmetric, but we fit it with a Gaussian anyway, and the center is then your radial velocity. Now, the reason that it's different is because we use a theoretical line list, which means that we can include things like the Landé factor and the magnetic sensitivity to each spectral line. So this is just the data coming out. I don't have time. So we are going to extend it. We are currently extending it and using our theoretical line list and the theoretical based information of the Landé factor of each of those lines in order to include that in our extraction process and hopefully get stellar activity down that way, because the majority of our stellar variability is governed by its magnetic field. So by including it in the extraction process, we hope to get out more stable radial velocities and at the same time, obviously, magnetic field variations. So stay tuned for that one. Now to end, I just want to very quickly plug HARPS 3. I've been involved in HARPS during my PhD, HARPS North, during my postdoc, so it only makes sense to be involved with HARPS 3, which is going to be the next one in line. This will not really be a copy, but more like an upgrade. We're hoping for 10 to 30 centimeter per second stability, so it really will be an upgrade. They're currently building it in Cambridge, so I can finally go and confirm that the instrument looks the way they claim it does, because I've always seen it in a box. What makes HARPS 3 will also be installed in La Palma at the INT. What makes it special is that with the HARPS 3 science team, we'll get 10 years of nightly access to the telescope. Not the entire night, because that would be greedy, but we get 10 years of nightly access, half of the night, and the other half will be up for open time. But the fact that we will have nightly access means that you will have densely sampled high stability, high precision radial velocities. The high stability, high precision, we can do that already. densely sampled, we can't. HARP3 will be the first one, and these are all the people involved, and it will be really, really cool for the first light in 2023, and then probably the first detections 5 to 10 years later than that. So stay tuned, and I'm just going to conclude by saying that the star is very important in exoplanet research, and if we do it right, we can potentially find another Earth. Thank you.
Thank you very much, Annelies. Very nice talk. Okay, so let me open the chat. So I suspect there will be questions. So if you have any questions, please mention it in the chat, and I will call out your name so it can be done in a more or less orderly fashion. I would actually maybe start myself. So the ZLSD technique, how does it compare to concerning the precision with existing techniques?
So existing techniques do, in essence, the same thing. So existing techniques do cross-correlation function is the mostly used technique. Most standard pipelines use that, where you also just correlate with a mask in order to get this average spectral line out. And, the difference is that they use observationally created masks. So they from well-observed stars, they extract a mask from that, and they use that on all stars of similar spectral type, whilst we retain the theoretical information in order to then take it a step further and include all types of other information. So the basics of ZLSD without including the Landé factor is relatively similar, even though we already outperform the standards. So the blue is the CCF technique and the orange is the LSD. So whilst it is roughly similar, we do already improve it with a couple tens of centimeters per second. It's not due to the technique, probably. It's probably more due to the fact that the pre-processing of the spectra is just more carefully handled. But it allows us to extend it further. That is the difference, mainly.
Okay, thanks. Anyone else have a question? Yes, please. Denis.
Hi, Annelies. Thank you for the presentation. Very nice. I have actually two questions. The first one is about the plot of Chen Kipling that you showed and the correlation between the mass and the radius. Mm-hmm. I was surprised to see that plot because in the paper there is another plot which shows a really clear correlation between mass and the radius, and 4 different regimes for the mass-radius relationship. And so I was surprised to see that plot, and I was wondering whether it's a new result or.
It's not a new result. I very literally just plotted the currently known planets and overplotted what they found in the paper. The difference is, of course, that they took a lot of care in biases and whatnot, etc. So, which is why it looks different, because the basics underneath are different. I also didn't include error bars on this. I just literally overplotted. I don't think they put the low precision ones, they never included in their modeling. So it's literally just going to the database, overplotting that relation. But yeah, it doesn't. It's just not that simple. We speak of a mass radius relation because it would be really cool to have one, because then you don't need 2 techniques. And at a certain level you can. So you can somewhat, because we do use that, right? We do use this mass radius relationship between quotes to make a guesstimate of what the expected semi-amplitude would be for every transiting planet, in order to know whether it's worth it or not to look at it with HARP-SNORD. Because we do have from time to time very interesting transiting exoplanets. We run it through that mass radius relationship, and it says like, well, you're actually highly likely that this signal is 40 centimeters per second. Then we're usually not going to bother, because that's lower than our error bar. Okay. So we do use that relationship somewhat, but you can't use it to actually infer things like composition of your planet.
Okay. Thank you. And I have another small question. So you show the graph of the occurrence rate of giant planet versus metallicity. So the increasing occurrence rate. I was wondering, for how many of these giant planets do we also have metallicity measurements, and do these measurements correlate with the stellar metallicity or not?
Well, we do. These are actually measured. For all the ones in this plot, so this was done on a volume limited sample. So both stars that were looked for planets and we didn't find any, and then stars where we did find planets, all of them have been spectroscopically characterized and have this actual metallicity. The error bars on the metallicity is about 0.05, 0.1, something like that. But these are all actual measurements. These here as well from spectra. For the majority of those, we do have the alpha abundances as well. There's a couple papers from Vardana Dibekian in 2013 that show already some of these differences between planet hosts and not for giant planets again.
Okay, but this plot shows the metallicity of the star, right? Not the planet.
Yes.
Okay.
Yeah, for the majority of those, we don't actually have a density measurement of the planet because they're not transiting. These are radial velocity detected giant planets. So you can't actually have a density or a chemical composition for your planet itself. Okay. And the same here on the right, these are only transiting, in majority of which don't have masses yet. So.
Yeah, okay, thank you.
Okay, so the next one is David.
Hello.
Hey.
It might tie in with the last question, but in the presentation you mentioned astrometry being useful for getting mass measurements, but it's not good enough yet. Are you familiar with any upcoming technology or telescopes that are going to try to boost that up to a better capacity?
Yeah, well, Gaia. Gaia is the astrometric mission right now. But even Gaia will only be sensitive to these long period giant planets. So Gaia won't be able to do the smaller planets. So Gaia's prediction is that they'll still find thousands of exoplanets, but it'll be restricted to this over here. I know astrometry is mentioned here on the plot, but I can't, it's over here. There's only one detection claimed, but it's also, of course, Jupiter. So Gaia will bring thousands of exoplanets, but won't be able to push to small planets. I'm not currently aware, but that might just be me, of the upcoming ones. But yeah, it's just like imaging. It's a matter of pushing the techniques better, because the signal that you're looking for in astrometry is shockingly small. It is actually shockingly small for radial velocity too, and we do have better instrumentation for that. So yeah, Gaia will bring thousands of them, but won't push to small planets, unfortunately.
Okay, next generation then.
Yes.
Okay, any other questions? I actually myself one. So it's concerning HARPS 3. So you go to the order of centimeter per second, right? So, but how does this improve? I mean, to what extent does it improve the planetary mass? Because at some point, what dominates are not your stochastic error, but your systematic error, as you mentioned, for example, for concerning stellar activity.
Mm-hmm.
So is going to the centimeter realm really going to improve the planetary mass?
It'll only do that if we get better in modeling the stellar variability, of course. So that is one of the caveats that we do have to do that. So a lot of the people involved in HARPS 3 are stellar variability experts, because that is the thing that we additionally have to do, of course. But the other thing that you can finally do is, for transits, it doesn't matter what the distance is of your star. Well, the probability of actually transiting goes down with distance, but the signal itself is as deep because it's purely dependent on radius. Whilst for radial velocity, if you go to further, longer period planets, there is the relation with period as well as mass. So for the same type of planet, the radial velocity signal will get slower, and Earth around the sun is 9 centimeters per second, whilst an Earth in a 20-day orbit is easily a meter per second, and roughly. So the HERPS, by going to smaller precision and looking for longer, we'll finally be able to also get these very long period planets, because that was the other thing that you quite nicely saw in this beginning plot. Long periods we can find giants, but long periods we don't quite can catch the smaller ones right now, because we're talking centimeter per second signals over here, whilst long period giants, such as our own Jupiter, still gives you signal of 12 meters per second, which is why we are able to find them and not able to find them for small planets. So going to smaller precision does help to extend period range out, but everything is under the big caveat that we have to understand stellar variability.
Right. Okay, thank you. Any more questions? If not, then I will thank Annelies again. Thank you very much. Very interesting talk, and I hope you will in the future have some time to visit us in person. We would really like that.
Yeah, if I'm in Belgium, I'll try to give you an actual visit. I would have loved so too.
Excellent. Thank you very much.
Cool.